Welcome back, everybody. So, last time we talked about the concept of momentum, the amount of motion an object has. And we said that it's conserved, which means that it's neither created nor destroyed, or another way you can think about it is the total momentum that I have before a collision, for example, must be equal to the total momentum after. That total part is very important. We talked about how it's only the system momentum that's conserved, not, for example, the momentum of individual robots as they collide. Well, these quantities, these conserved quantities, are extremely valuable when we're talking about engineering and physics in general. And one of the most important ones that we're going to work with is conservation of energy. Well, before we can get to energy, we have to kind of understand what we're talking about. What is energy? You probably have some idea of, well, energy is this. It's something that's powering things or whatever. So, in order to use the concept of energy in an engineering environment, we have to know precisely what we mean by that. So that's what we're going to start off with in the lecture today. Let's get started. Okay, so look in your book under work and energy here. Microtask 1, we're really just wanting you to kind of come up with your own definition of energy, some non-sciencey definition. What do you think energy is? Not in science terms, but just in general, everyday people kind of language. Pause the video and think about that, because coming up with these concepts is actually pretty important. Pause the video, you may say, no, Dr. K, I can keep going with that. Really working on trying to get these concepts going. Okay, well, there are all kinds of possibilities. Energy is something that makes things move, or energy is something that provides heat, or energy is something that's pushing the electricity through your lights, things like that. Well, to get a formal definition, we have to be a little more precise than that. And so if you look down in the first column here, energy is the ability to do work. Energy is whatever I have that lets me do work. Okay, that's not a terribly good definition because we haven't defined what work is. And we can't use a definition that uses a definition we haven't defined, right? So the first thing we've got to do is we've got to come up with some definition of work. Now, you may think doing physics is work. It's fun. It's not work. You may disagree. That's okay. But you may think that pushing against a wall is work. Well, in some cases it can be, in some cases it's not. So let's come up with a very precise definition for it. And if you look right below that energy definition, you're going to see there it says work is a change in momentum that's made over a certain time interval and in a certain distance. All right? So the big thing is that work is a change in momentum. That's the key. If I can change the momentum of an object, then I have done work. This means that technically momentum isn't going to be conserved because I'm putting momentum in from outside of my system, or I'm taking momentum out of my system. And so the system momentum may not be conserved because some of it has left to an area that I'm not tracking. Now, realistically, that momentum has left as work or has come in as work. And if I were tracking everything in the universe, I'd still be able to follow it. But for obvious reasons, we can't do that. So if I want to speed something up, let's say I've got a robot that's just sitting still, and I want to make it start moving. Well, I have to change its momentum, right? Because initially the total momentum of the system is 0. So somehow if I want my motor to get that thing to change its momentum, give it some velocity, then that motor has to do work. And that's what we're talking about with that. So you can think of work as being the exchange medium of energy. So if I want to make my robot start moving, well, I want to give it some energy of motion. We call that kinetic energy for the same reason that we talk about kinematics. Kinetic just means motion, that's all. So kinematics was the description of motion. So if I want to give it some of that kinetic energy, then my motors have to take the chemical energy from the battery that was stored in the battery and then use that energy to do work on the robot, which then gives it kinetic energy. It's actually impossible to take one energy directly into another energy. You've got to do some sort of work in the process. Now, we will idealize that a lot of times by simply saying, oh yeah, I took my battery energy and I converted it into kinetic energy, because that work part in between is just that transition. That's the exchange of what's going on. But it is the work that's giving it that momentum, that's giving it that motion. So we need to come up with some sort of a mathematical shortcut, a mathematical definition for work that we can use to then figure out how much energy and therefore momentum that I've given to the system. Well, you see in our definition, there are three things that we care about with this. There's going to be a change in momentum, but it also matters the time interval over which I apply that. And if you think about that, if I do a very short time interval, right? If I take the same amount of oomph in it and I apply it over a very short time period, that's going to make it go faster than just going lighter in that same amount of time interval, right? So, or taking the same amount and then pushing it over a slower time. Same thing with distance. Let's say that I'm applying the same per time, I'm giving that same momentum change. The longer I apply that energy, that work over it, then the more total work that I'm going to do. So those are the three things that we're going to look at. Okay, so now we're going to look at each one of those three variables, and we're going to decide, are they directly proportional or are they inversely proportional, just like we did with momentum. And this technique is how basically all of these mathematical equations of physics are figured out. We just simply look at the system and say, okay, if I increase this, what happens to this? So stop the video and think about it. Which do you think would produce more work? If I give it more momentum change or if I give it less momentum change? Well, in order to get a bigger momentum change, I've got to do more work. So they're going to be directly proportional. So go ahead, let's switch to pen here. So go ahead and circle that in your book so that you've got that. All right, now in the same manner, I want you to go ahead and do the next two. So pause the video, think about the time interval. How much work is necessary to do something in a very short time interval? Does it take more work or does it take less work if I want to make that change in a very short time interval? And then the next one that we want to look at then is, how about the distance? How much work does it take to make that momentum change over a larger distance? Does it take more work or does it take less work? Okay, so coming back to that then, if I want to do that same amount of oomph change in a shorter time interval, I'm going to have to work a lot harder, aren't I, than just doing it over a longer time interval. Same thing, if I'm going to have to apply that work over if I'm going to try to do that momentum change over a longer distance, well, then I'm going to have it be directly proportional. I'm going to have to put in more work. So the next thing we do then, once we've decided directly proportional, inversely proportional, is we put these things together in order to form our actual equation. So remember that if it's directly proportional, it goes in the numerator. If it's inversely proportional, it goes in the denominator. Now, I am going to write this as delta W, a change in work. That's not technically correct because work is a change, right? It doesn't make sense. I can take my robot and I can say, okay, this robot has this temperature, right? You could actually measure that. You could say this robot at this point has this mass. I could say it has this much energy. What I can't say is it has this much work. That doesn't make sense. Work is something that's causing that change in the energy there. So work is always inherently a change. So saying delta work, is my change in work, and that's not really correct. The work is the change in energy. But let's leave it here for now, just so that we can, right now I'm going to explicitly put the delta W, just to remind us that work is a change. But when we actually write work, we're just going to have that W there. Okay, so we know that it's going to depend upon our momentum change, not just the momentum, but the change in momentum. So that's going to be delta P, change in momentum. That goes in the numerator because it's directly proportional. Now the time interval, delta T, the change in time, is inversely proportional, so it has to go in the denominator. And then my distance, my change in distance, again, that's delta. It's directly proportional, so it also goes in the numerator alike. So, and it is a vector. Okay, now we've got one little bit of a problem here. Work doesn't actually have a direction, right? It's just how much you put in. Same thing if you think about temperature. There's no direction to temperature. If my temperature may increase, sure, and so the change may be positive, but I'm not going to have a temperature in a particular X, Y, or Z direction. Same thing is true of work. This is just the amount of energy that I put into that. So work itself is a scalar, and we're going to highlight that specifically on another page. But here I've got two vectors. Anytime I'm multiplying two vectors, I can't actually just multiply. I have to either use the scalar product, which you probably call the dot product, or the vector product, which you may call the cross product. Well, if I've got two vectors and I want to get a scalar out of it, I'm going to use the scalar product, the dot product. You see why engineers tend to refer to it as a scalar product, because, well, duh, you're going to get a scalar out of it. Okay, so that's my general equation here. Now, if I want to get an explicit definition for work, then I'm going to want to add up all of these little pieces over the entire time. Now, here's something that may be new to you. Let's say that I've got a robot that starts here and another one that starts here, and this robot has its work applied to here. So I went from this distance to this distance. But this robot went on this path. It ends up at exactly the same spot. Which of these robots would have had to have done more work? Yeah, the one that took this twisty curve. It was having to apply work over this entire path here, which is much longer. You can almost think of it as the distance traveled versus the displacement issue. Work is not a vector, it's a scalar. So I can't just talk about, okay, what was my energy here and my energy here? In order for the whole path, I have to apply that work over that entire path. So what I do is I take very tiny little pieces of this path and I add them up. Okay. Now that is not the same as doing your standard integral. Here's a good example. Let's say that I have some sort of path that goes like this. Okay, and I'm going to start this at 0. Well, if I had just a standard integral, you know, maybe it's something d theta or whatever, I would go from 0 to 0, wouldn't I? And so the end result then, when I take that integral, is just going to be 0. But obviously I did travel some distance. I did some work along that path. So I can't use this standard integral. So instead we use what's called a path integral. So I'm going to rewrite this with this symbol. This is a differential, but it's a path-dependent differential. And then these, of course, are just going to be my change over in that instantaneous change in that path. Whoops, that should be, let's see. Okay. Well, now I'm going to take the path integral of both sides. So rewriting that down here, I'm going to take the path integral here and the path integral here. This symbol right here that you see, this means the path integral. You may have seen that as a circle integral or a line integral or something like that. That's just a specific case. This could be over any path in any number of dimensions from that. So taking the path integral of this differential, which I'm going to draw that a little bit better, it looks kind of like that, gives me my W. Remember that this work is still a change. It's the change in energy, right? But now when I take the path integral over this change, then I'll get something that looks like this. But I can't integrate that. I can't integrate that for two reasons. One, I've got two vectors. I've got to get rid of the vector. I can only have those scalars in there. The second thing is that I've got three differentials, and I can't do that either. So somehow I've got to come up with a definition then that allows me to get rid of all this so that I can integrate these. Then my change in energy then is going to equal my work, which is going to equal this, dp dt dx, right? Because we said that how much my energy changes from here to here depends upon how much work I did from that. So my change in energy is my work. And so you can see that work is kind of a change, right? Even though we don't have the delta in front of it. All right, well, my first step then is to get rid of this dot product. Now, just to remind you of the dot product, if I have two vectors, a dot b, then the value of that is going to be their magnitude times the cosine of the angle between them. If you've taken this in calculus, you probably heard something like a projection. So if this is A and this is B, then the dot product is the projection. So this length right here of A onto B. Well, that angle between them is just theta, right? That's the angle between them. And so just using geometry, you should be able to see that if this is my hypotenuse, if A is my hypotenuse and B is my adjacent side, well, the adjacent over the hypotenuse is just the cosine of that angle. So that's where this comes from. And you should make a flip book in your page for vector multiplication. This is going to be our first one. It's going to be that scalar product. All right, now my change in momentum must be equal to my change in x. The vectors are not the magnitudes, but the directions. They have to be in the same direction, right? If I push something in this way, its change in displacement is going to be in that same direction. So if the angle between them is 0, they're in the same direction, what is cosine theta? Well, cosine 0 is just 1. So in this case, I'm going to go ahead and write it this way. Delta p dot delta x, or dp dot dx, then is simply dp dx, where these are magnitudes now. dt. So that was my a vector, that was my b vector, and technically, yes, there's a cosine theta here, but since theta is 0, the cosine of 0 is 1. So far, so good. Okay. Now, I want to get an expression for this. Well, I've got a lot of things that are changing in here. So what if we grouped these two together, the dx over dt? So I've got a dp, and now think back to what you've learned up to this point. What is dx dt? That's my velocity, right? So that's going to be dp times the velocity here. And neither one of these are vectors at this point. Now, you're probably much more comfortable if I write it this way, right? That's probably the way you're used to seeing it in your calculus classes. All right, so you may say, well, okay, v is a constant, right? So I'll pull it out and I'll integrate with respect to p. However, the momentum is a function of the velocity. Embedded in that symbol is a velocity, isn't it? So the v actually does depend upon p, so I can't pull it out of the integral here. So what I'm going to do is I'm going to substitute in for p. I'm going to say delta E is equal to the path integral of v, and then let's put that in the parenthesis. There we go. Of d mv. And again, this is not a vector, right? Because we're just taking the magnitude of the momentum there. All right. If m is not a function of v, it doesn't necessarily have to be constant. It just can't be a function of v. Now that means usually it's constant, right? But let's take that special case. In the special case that m is not a function of v, or you can equivalently think of it if m is just constant, because then it's certainly not going to be a function of v, then I can pull it all the way outside the integral, right? Let's erase some of this to give myself some room. All our little marks here. There we go. Okay, so I'm going to pull that all the way outside the integral. So let's do that. That's going to give me my change in energy is going to equal the mass, which again, we're assuming is going to be constant or at least not a function of velocity. And then that gives me v dv. And that is probably something you can integrate. Pause the video. Let's see if you can do that integration. Okay, so I've got delta E is going to be equal to m times 1/2 v squared, and then getting rid of my dv there. 1/2 v squared. Now, this then is going to be evaluated for my energy change. My work is different all the way through, but my energy change along that path is going to be going from one velocity, my initial velocity, to my final velocity. So if I write this out, I'm going to go ahead and take this delta E. You should be able to agree that that's just my final minus my initial. That's the change. That's our definition of our difference, of our change in. That then is equal to, pulling the 1/2 out, VF squared minus VI squared. Right? Okay, so if the object is not moving, if its velocity is 0, how much energy of motion does it have? None, right? It's not moving, so therefore it can't have any energy of motion. So this is not an assumption. This is just a physical fact. If VI is 0, then EI is also 0. You see where we're coming from with that? That's just a physical fact. If it's not moving, it doesn't have any energy of motion. So my final energy then is the actual energy that it has, this energy of motion. Now there are many different types of energy. We're going to talk about that in a minute. So since we're talking about energy of motion, let's put a little K subscript here so that we know it's the kinetic energy, since kinetic means motion. And then all I'm going to be left with is 1/2 m, whatever velocity it has, squared. And that is my definition of kinetic energy. That's how much energy of motion I have. And it depends solely upon the mass and the velocity. But notice that it's a scalar. So this has some huge advantages over trying to solve other types of problems. So we could use, if I want to get a final velocity, for example, I absolutely could use the kinematics equations and figure out its final velocity. But that's a vector. I've got to do the issue with the acceleration. I've got to figure all of that out, and I will get there, right? On the other hand, think about if I had this marker or this pen right here, and let's say it's sitting on the ground. If it's just sitting on the ground, does it have any kinetic energy? No, it doesn't have any energy at all, right? So I reach over and I put work into this pen because it's coming from my body, right? My body is doing work, and so I'm putting energy into the pen. Well, now does it have any kinetic energy? No, it's still not moving, right? So it doesn't have any kinetic energy. Where did that work go? I put some energy into it. Well, if I release the pen, if I let go of it, what's going to happen to it? Now it's going to get some kinetic energy. You can see that it's going to fall, and so it's going to get some kinetic energy. So there must be some energy stored in that pen somehow. And in fact, what happened is I did work against gravity. So I stored some energy by working against gravity. If I were way, way, way out in space, far from any gravitational sources, if I picked this up, right, I wouldn't be doing any work. I'd just give it a kick, and it's just going to keep going forever. And I'd actually have to do work to stop it from moving anywhere. You see that? So it's gravity that I'm doing work against. So we would call it a stored energy, we call a potential energy, because it's got the potential to do work. When I let go of this, right now it's got no energy at all, or no kinetic energy. It's got gravitational potential energy. It's got that stored energy. If I let go, that stored energy gets converted into kinetic energy. Gravity is now doing work on the pen. So I've got stored energy then, gravity is doing work, and that's converting, that's taking out its stored energy and putting in its kinetic energy. So that at the instant it hits, so it's falling, and the instant it hits, how much gravitational potential energy does it have? None. It's used it all up. However, it's got an impact velocity, doesn't it? It hit hard. So that means all of that potential energy was converted into kinetic energy. So if I was able to figure out how much potential energy it had here, I could figure out what its impact velocity is going to be. One of the things you're going to be doing in lab is you're going to be doing just the opposite. You're going to have a cannon, and you're going to launch that thing forward. You're going to launch it straight up. Once you figure out how high it went, then now we know once it's at its maximum height, if it's at apogee, what do we know about its velocity? It's 0. So if my velocity is 0 here, my kinetic energy is also 0. So I give it some initial kinetic energy as I launch it out of the cannon. It goes up, up, up. What's happening to its kinetic energy? It's decreasing because it's going into the stored energy in the pen. So the height at which all kinetic energy is gone that tells me how much stored energy I have. Does that make sense? So if I could figure out how much stored energy is here, I also know how much kinetic energy I had to start with, because it's conserved. The total energy of the system is conserved. So it just gets traded around using work. So if I know this, how much potential energy I had here, I know how much kinetic energy I had when I launched, I can now calculate the muzzle velocity, the launch velocity of this cannon. And you can do this with your robots, with spring cannons. In the lab, you're going to be using, a circus cannon for launching things up, things like that. But this is much, much, much faster than trying to do this with kinematics. You can do it with kinematics and it will work. But if you can do it with energy, always do it with energy, because you don't have vectors. It's going to be faster. Now, there are some things that the kinetic energy or any energy method can't give you. One of those is the time that it takes to get to the top. There's no way for the energy method to tell you the time. You've got to use kinematics for that. You don't have a choice. So there are a couple of other instances where you simply can't use the energy method, but if you can, it's always going to be faster. All right, so let's look at the next page. And here we're formally talking about what we mean by conservation. Remember, this delta of some quantity equals 0. That means that quantity is conserved. So the energy is conserved. But as you might expect with what we saw with the momentum, the individual energy is not conserved. Thinking about our pen, I started out, if I launch it up, I've got some kinetic energy, but by the time I get up to here, its kinetic energy is 0. So certainly that has not been conserved. Instead, the system energy is conserved. So the total energy is conserved. So remember, we can write that then as my total energy final minus my total energy initial is 0, which is the same thing as saying my total energy, that's a total, final is equal to my total energy initial. Now, if all I have is kinetic energy, then I can say, let's take our two robots, right? So here I've got these two robots, and they are colliding. So this robot's going this way, this robot's going this way. And so my kinetic energy for the first robot, let's say that this is m1 and this is m2, and it's moving with velocity 1 and velocity 2, and these will be its initial velocities, and then after the collision it'll have some final velocities. So this will be m1 v1 initial, but that is not a vector because it is squared, plus 1/2 m2 v2 initial. That's the initial total kinetic energy, and we're assuming that's the only energy in the system. And then afterwards, it's going to be this, v1 final squared plus 1/2 m2 v2 final squared. So that then is a way of saying conservation of energy. Think back to the momentum problem we had where we didn't have enough information, right? If they bounced off of each other, I only had one equation for conservation of momentum, and then I was like, well, but I can't find both the velocities. I either need another equation or I need some more data. Now you have a second equation. We're going to look at this in more detail when we talk about elastic collisions, but this equation is giving you that extra equation that you need to solve this problem. So you can solve it without having an extra sensor. Now, remember, there are other types of energy, and we've got some of them listed right here. Kinetic energy is not the only kind. We've already talked about gravitational potential energy. That's stored energy. Now, here's the symbology that I'm going to use. If it is a stored energy, I'm going to use a U. If it is basically any other type of energy, with a few exceptions, I'm going to use E. In both cases, I'm going to have some sort of subscript. So my gravitational potential energy, I might say, is UG. My kinetic energy, I might say, is EK. I can also have energy stored in elastic potential energy. So that could be a spring, it could be a sure enough piece of elastic, anything like that. So you could write that as this to stand for elastic. Well, we also have electrical potential energy. We can have electrical energy stored in here. And people sometimes get confused. So you will find people who do this. They'll put an S because they'll say it's spring energy, even though it might not be a spring. It might just be, a piece of metal bending is still going to have that elastic potential energy. And then there are a number of other types of energy. I might have sonic energy. I might have thermal energy. Now, oftentimes we'll use the special symbol capital Q for thermal energy, but we'll get to that another time. One kind of energy that you may not be familiar with is this last one, this deformational energy. Look up at the top right here. Deformational energy is the energy that goes into rearranging molecules. So let's say my robots came in and they actually bent before they moved by. So they crashed their bumpers. Damage was done to those robots. Nothing fell off. Everything is still in the robot, but it bent it. Well, it took energy to bring your molecules from here to here. That energy that's required is the deformational energy. So we typically use the symbol that. WD, so the work done deforming the robots. So if I were going to write this out, I might say, okay, I might have some gravitational potential energy initial, and we'll do this just for one robot for now, some kinetic energy initial, and then that's going to equal to whatever my gravitational energy final was plus my kinetic energy final. And remember, I could have UG1I, UG2I, EK1I, EK2I, and so on and so on. All right. Well, we need a sign convention for work. And the sign convention is that if work goes into the system, we say it's positive. Don't get confused. It's not a vector. We're not talking about a direction. Just because it has a positive or minus in this case doesn't mean that it's got a direction. So instead, what we're saying is if energy goes into the system, we're going to say it's positive. If energy comes out of the system, we're going to say that the work is negative. And this is just like having a temperature. Temperature is a scalar. It doesn't have a direction, right? But my change could be in the positive or it could be negative. If the number gets bigger, it's a scalar. If the number gets bigger, we say that it's positive. If the number gets smaller, we say it's negative. Well, work is also a change. So if I'm adding energy into the system, it's positive. Energy out of the system is negative. And that will always work. So for example, I might say, oh, okay, I lost some of that energy to deformation. So since it was coming out of the system, then I would make that negative, and this would be correct. Now, however, the way I think of it, and this is entirely up to you, but it makes sense to me, is if the energy is going into the system, I put it on the left side, on the initial side of the equation. If the energy is coming out of the system, I put it on the final side. If you do that, it's always going to be positive. Whoops, not friction, but how about deformational energy? It's always going to be positive, right? So, and you think about it, if I had my negative over here and I simply moved it to the other side, of course it's going to become positive. But the reason why I like this is it makes sense physically to me. This is how much energy total that robot had initially. When it came out, it had less of this because some of it went into deforming the robot. And so this makes total sense to me. I now see why the velocity might be less. For example, if our robots are on the same, are both on the ground then, right, they don't have any gravitational potential energy. And so let's go ahead and put both robots in here. My EK1 initial plus EK2 initial must equal EK1 final plus EK1 final plus however much work went into deforming the robots. If I know their initial and final velocities, I can actually figure out how much work went into deforming the robots in that case. But think about it. This is how much, this is related to the mass and velocity that they had initially. Their mass might not have changed, but because their velocity changed, it might turn out that this total is less than you would expect it to be. And the reason for that is some of the energy went into deforming the robots. Okay, so looking at this last page here then with microtask 3, we're just summing up some things here. Does momentum have a direction? Sure, right? I can have a momentum forward, I can have momentum backwards. Later on, we're going to be in 2D where I can go in both horizontal and vertical direction, for example. If it has a direction, is the momentum a vector? Sure. Does kinetic energy have a direction? And this may, you gotta think about this a little bit. I have the same amount of energy, whether I'm going forward, backwards, however I go. Energy is just, you just point at it and you say, hey, that's how much energy is contained in this thing. So in this system. So there is no direction associated with it. Therefore, kinetic energy cannot be a vector. It's got to be a scalar. Now let me give you one last little thing we may eventually work on. Let's say you've got a roller coaster that goes like this, and it's this crazy, crazy loop. This would come up over and then plummet down. So up here, before the robot starts moving, it doesn't have any velocity at all, but it does have some stored energy. It's got some of that gravitational potential energy. So we can spend that to get our kinetic energy. So once the robot's here, right, it's moving at some crazy speed because we're going basically straight down. So it now has some kinetic energy. We can figure out exactly how much kinetic energy it has by figuring out what its new gravitational potential energy is, because the difference between these two must be equal to the kinetic energy. No, I don't have to do any kinematics. I don't have to know any accelerations. Everything just works out. Right? So this is just one example of the power of using the energy method. One last little tip I'm going to give you for your homework. Let me get out of this one right quick. One of the homework problems that you have, you're going to be trying to figure out the work done when a raindrop falls from a cloud. So here's our cloud, and he's very mean cloud, right? Because he's a thunderstorm. And let's say I've got this raindrop, and we give you a mass for the raindrop. And then that raindrop falls all the way down to here. And so we give you this height as well. So we give you the mass and we give you the height. I want to know how much work is done. Well, if we go back to our original definition of work, then that's going to be delta P, delta T, that should be delta X, because I'm just looking at that total. So I've got delta H, right? H is delta X. My momentum, I'm going to need to know, I know the mass, but I'm going to need to know what my final velocity is. My initial velocity is 0. I started up here. And then I'm also going to need to know how long it took. So kinematics will get you there. I've got a constant acceleration. What's the acceleration in this case? My acceleration in this case is just the acceleration due to gravity. So you use your two kinematics equations, one to get the final velocity based on the distance, and just to give you a clue, that would be this. Right, where this is 0. And then I would need to find the time. Well, if I know my final velocity and I know my initial velocity, then I can get my time this way, and that of course is going to be g. So then this is 0. Now I can solve for that time, that elapsed time. And it will work. 100% will work. However, there is a faster way. We can do this using work and energy. So let's go back to our original equation here, the one that you would be plugging in the values you found using kinematics into. All right, so I've got work is equal to, let's just go ahead and use our integral form. We can keep it as averages. Let's just keep it as averages, just like we did before. And so that's going to be dp dx, or delta x, sorry, over delta t. Well, let's do a little bit of rearranging. Work then would be equal to delta m v delta x over delta t. Pulling my m out then, I get m delta v over delta t times delta x. Does this look familiar? Well, delta v over delta x is the average acceleration, but the acceleration in this case is constant. So my acceleration is just g. So now I have nothing but constants. If I integrate this delta x from 0 down, let's make my positive direction this way. So I integrate my delta x from 0 to h, then I'm going to end up with the work done being mg, both of those are constants, h. Just like that. And this is exactly the same result you'll get if you use kinematics. This idea of conservation is critical to everything that we're doing in physics in general and engineering in particular, because it turns out there's a lot of things in nature that are conserved. And so that gives us a way to track what's happening with a spacecraft or a robot or anything else that we want to work with. For example, if we know that energy is conserved, we know that energy is going somewhere. As a spacecraft is re-entering into the atmosphere, we want to get rid of that kinetic energy. We really don't want that spacecraft coming in at 11 kilometers per second or something like that. So we count on losing energy to friction from the atmosphere as it comes in and slows it down to a speed that's going to be safe. That's just one example, but this type of analysis pervades everything that you will end up doing in engineering and in physics. So it's really important that we look for these conservation laws and then use them whenever we can. We'll see you next time.